call numbers and he was like morons.
No, it was like 0005. Like it was like really basic. Yeah. And he was like, "Oh my God, are you kidding me?"
That's a really common one. 911. I don't know why people.
I found my copy of QED. Let's go. Let's get smashed.
You can tell like a character.
Look, here's the part where he tells everyone that Photon sucks and no one knows why. I'm kidding. That's the entire book.
Seriously. So, here's what's going on. This month is crazy.
Oh no.
It's also crazy in this class in particular because we have to get done in time for the Fermi script, which is what? We were going to prove that next semester. That was all our problems, I'm pretty sure. The good news is the Fermi script itself seems to be going fine. The first they didn't think they'd be able to get everyone into V0, but now it looks like they will, so that's great. At first we were too big, but then like 2 people dropped and somehow that fixed everything. So yeah, don't ask me. I was like, you're like, oh no, that's fine, everything's fine now. And I'm like, okay. So that's good. So that part's all going well, but we actually have to have something to present then, right? So that seems useful. So and Dave, you're still able to make it? Great. Good. So like what we need to do now is get the detector ready. So there's one more part of the detector that I gotta get ready first. I am not happy with the way the schedule looks. I have not been able to find a way to fix it yet. Okay, I don't like the way it's too fragmented with the physics learning, but like I have not been able to find a way around it because of all the other things. The Thanksgiving super early this year. So that makes it Thanksgiving. I always do it right after Thanksgiving, so that's when I find the least likely that a teacher will have a major assessment due. But when Thanksgiving's early, that means that we have to finish early, right? And it just makes it more complicated. Okay, current plan. Today I'm going to tell you about neon detectors. That is due Friday. There's really no leeway on this. It has to be due Friday. Good news is, it's basically the same as the tracker, okay? So like, you shouldn't have to learn anything new. Just a few little details I'll throw you right now. As a result of that, today is the only class day you'll have to work on it. Okay? It's not like super hard, and last time I did this, it seemed to go okay. So I'm hoping that this remains okay. Neon detectors are kind of the easiest and least important kind of part of the detector, so like you can go a little easy on it. Now, current plan of my schedule is to have what I currently have the schedule is to have the quiz on this, so the rest of this week will all be on quantum mechanics material, quantum stuff. The quiz for that I have scheduled for Monday. I may possibly switch it to Tuesday, but if I switch, then I'm switching it with another detector assignment. So, right, I'm trying to work out what's going to work best. I'm trying to get something that works well for you guys. I don't like fragmenting things like between the detector and the physics material. But the schedule is kind of putting a lot of pressure on it. So I will see it right come up. Okay, so the next 3 days will be material. The quiz will be either Monday or Tuesday. And next week also you will have to put in your final sort of advertisements for your detectors, so we can put them out and vote. And then once we vote, then we'll have to do all the work to design the final detector. Everyone will have something to do, don't worry. And everyone will put together the final detector and the final detector assignments and the final slides will be due before the break. Okay? So it's a little bit crazy. I don't like it that way, but with the early Thanksgiving, my missing days at the conference, all the other things, it's what we have. We got to get it done in time. Got to have something to present. Okay, so Fermilab is the 7th, I think? Yeah. 27th? Okay. That trip is up to you to make sure your teachers are aware. I've already put in the paperwork and stuff. You need to make sure your teachers are aware of the fact that you are leaving. That is your job. In particular, watch out for presentations. Usually there's no test the day after Thanksgiving, but there might be presentations. If there are presentations, there's usually leeway, let's say, the ability to shift it to a Tuesday instead. So see if you are able to do that, or Thursday, to another day instead. So it's up to you to talk to your teachers to see if you're able to do this. This is an absolutely essential mandatory trip. And I do not like pulling people out of class because of SMR. I can't do it on Wednesday either, so we have to do do this. Yeah.
Is it going to be the entire?
It is. You should plan on the entire day being gone. You may make it back for a day.
Are we leaving first?
We are not going to make first month. Yeah.
Is this something we dress up for?
Say it one more time. No, this is stuff dress up for anything. The most I ever dressed up was when I gave an invited talk at a very prestigious conference. When I was finishing grad school, they selected me for a very prestigious invited talk, and there I dressed less nicely than I dress right now. No tie, it was ridiculous. No one took me seriously at the time. And so yeah, physicists do not dress up, so don't worry about that part. That's a good question. So, but the most important thing is to make sure things are clear to your teachers. Okay, that is your responsibility. I put in the paperwork and stuff, but you have to make sure it's clear on that last day. Okay, if there are any questions, of course, they can talk to me. Okay? Good. It'll be a fun trip. I'll give you more details later. Let's talk about muons. Okay, so what did I say was the issue with muons and calorimeter?
They don't interact.
They don't interact. It's not like they don't interact. It's go ahead.
They're too fast. They don't
It's not
stop.
like they're too fast.
They don't
Yes.
stop.
So do you remember the exact issue? Go ahead. Right, they're massive. So unlike an electron, they're massive. Electrons are very low masses. They like disperse their energy very quickly. Muons have 250 times the mass of an electron, 210 times the mass of an electron, and therefore are a lot harder to bounce around, right? On the other hand, protons, so that's the same problems that protons and other heavy particles have. But how do the protons lose most of their energy? What do they hit? You remember? They're in the H column, yeah. But what is the H? What kind of interaction? They have nuclear interactions with the strong force, right? So they hit a nucleus, and so it doesn't happen that often. But when it hits a nucleus, it blasts it and it loses a lot of energy in doing that. So that's how protons and neutrons and pions lose their energy. But what's the issue with muons there?
No.
They don't interact. They have strong interactions, so they don't have that kind of effect on a nucleus. They hit a nucleus and they kind of bounce off and keep going. So because of that, it is basically impossible to stop a muon. Okay, there's really no way to do it. I mean, eventually, of course, it'll stop, or really, it'll decay because it's an unstable particle, right? But it's going so it has so much energy that it gets a Lorentz boost factor, so it'll take actually quite a while to decay. So as a result, there's like nothing you can do to block the muons. Okay. So, what do we do about them? What? Go ahead.
You bend it.
Well, yes. Well, we already did that, right? Because in the interior of our detector, we had a tracking titanium, remember? And there was a magnet around it, a solenoid, right? And here we had tracking, and so the whole point of that was that it would bend like that, right? It would bend, and you could use the curvature to measure the magnetic field. And the curvature to measure the momentum. Remember that? I hope so. We'll have to do it again. And then around that, we put the E-cal. Then around that, we put the H-cal. Okay? Now, by the end of the H-cal, what has happened to everything else? It's been stopped, right? Everything except for muons and neutrinos, I don't see those. So everything except for muons has been stopped. So what you have out here is actually a golden opportunity. Because while it's true that you can't actually measure the energy of the muons directly, what you do have is a region where there's nothing but muons. And you can and you filtered out all the other junk that was shooting out of your detector, especially all those jets and stuff, right? Are all kind of filtered out. And anything that shows up over here
It's a muon.
So we don't like the word death.
trigger word. Trigger warning. We're going to mention jets clustering, energy deposition, gamma functions. All right. So
Can I take a stress one?
So basically, anything that shows up here is a muon, right? It does particle identification for you just by being there. So what we do is we set up detectors out here that that just detect the particle. Now the simplest version is we just detect if there's a particle there. If it's there, it's a muon. And you can connect it to the previous track. And if you see it here, this is a muon. And if another track, goes like whatever, and there's nothing, then it is not a muon. Right?
Mm-hmm.
Okay, so we can use this as a particle identification device, which is very useful because it also gives us real nice clear, like that's definitely a muon, and then you can kind of help understand the rest of it. Yes.
So you said that muons and neutrinos are there, but
No one can see neutrinos.
Because like the charge, like it doesn't activate.
They're neutrinos when they're charged.
Yeah, so like they wouldn't activate the baseline.
They don't activate anything. Yeah. The neutrinos interact with basically nothing. They're never visible unless you have. The neutrino detections we have detect like 1 in a trillion. Like we don't, you don't really see them. Yeah.
What do you get to that thinking about it?
What a great question. Jay brings up a good question. Yes, you could have things that are not muons making it through the H canal, particularly high energy pions, for example, produced lately by jets somewhere around here, can sometimes be called punch through and get through the H canal. So one thing about the muon detectors is the problem, they call them fakes. Okay, or they call them fakes because they're not really muons, they're fake muons, right? So the problem with fakes is an issue. They come from punch through primarily, right, where a particle punches through the calorimeter. There's so much energy you can make it through. So what's one way you think you could stop that, or at least reduce its potential? Sure. So one thing you could do is just surround this thing with more shielding, right? But there's actually a very good candidate for what shielding to use. That's this. Okay, this thing is a giant magnet, right?
Yeah.
Okay, you guys probably haven't studied E and M yet, but magnetic field lines go in circles, okay? So if the magnet is a solenoid, the magnetic field goes through it this way and then loops around like this. This is a problem, because then there's a magnetic field here, but there's also a magnetic field out here, right? And you kind of don't want a magnetic field outside of your solenoid, you want it just inside, because it'll mess everything up outside. Right? It's much harder to build in a magnetic field environment. So what you do to avoid, and this causes also makes magnet harder to build and a bunch of other things. So what you do is you put a big chunks of iron, and what iron is ferromagnetic, and basically it means, roughly speaking, magnetic fields really like it. Okay? This is a not so technical description. Magnetic fields like iron, they suck up all the magnetic field, right? So the stuff that would have been kind of going this way diverts towards the iron instead. It just likes the iron. Okay? This iron is referred to as return yoke. Wow, yoke. There we go. Okay, they call it return yoke. It's the return from the magnetic field. It lets the magnetic field return so that the magnetic field goes to the iron and not through your detector. And therefore you're safe. You don't have to worry about it screwing up everything else. Now, if your detector has iron in it, that's fine too. It's no big deal. Because the magnetic field still going through that and not through your sensitive electrons, which is wrong. Yeah. Oh no, you still need to return yoke. Because the amount of iron you have is probably insufficient. So typically, virtually every detector has a big chunk of iron around it. Iron's pretty cheap, as you discovered, right? And it has to be iron, right? It has to be ferromagnetic material, which means iron. So no brass or lead or anything else. It has to be iron. Nickel and cobalt are not sufficiently ferromagnetic and way more expensive.
What about Oz?
Skim milk. Then you call it skim fluid, right? All right, so this is one thing where you can really kill two birds with one stone, right? And this is a standard detector design. Is put your return yoke outside the calorimeter, then it's doing two things. First of all, it's sucking the magnetic field back, which it needs to. And secondly, it's now providing shielding so that anything that does punch through the H canal now has an additional layer of iron to punch through before it can make it in, thus reducing your fake rate. Okay? The rule on it I haven't written down, but it's 0.1 meters per Tesla is the thickness you need to suck up your return yoke. I mean, to suck up your return magnetic field. Okay. So, depends on the strength of your magnetic field, how much you need. But, you could always add more if you just want a little extra shielding. Right? Especially if your H cal wasn't super thick or something. Like if your H cal was only like 20 interaction lengths, then you can stick a little bit more iron on there, then you can deal with it. You don't have to worry about your H getting through. Okay? Alright, good. So that's one problem solved. Let's now assume that everything we see, there's always a possibility of fakes, but we're going to have a very low fake rate now. We got to keep an eye on it. Okay, good. Now, what you do is you can see it, and you see a muon stub, and you're like, yay, they call it a stub. You see a muon stub, and you're like, yay, it's a muon, that's good. So that's the basic thing that you can do with a muon detector. Now, how do you actually detect it? Well, with anything you want. Muons are still charged, right? So what could you use? Pixels. Right, you could use pixels, but notice the issue with using pixels. What's the difference between building out here and building in here? It's a lot bigger. As a result, we're not using any silicon. I mean, you could, if you could somehow afford it. Like you could afford like this little tiny piece of pixel right here in the middle or something, I'm not sure. Probably, but think about it. Also, unlike here, what's the other difference about the tracks themselves? There's a lot fewer of them with only muons, and they're going to be a lot further apart. So you don't need that kind of micron level resolution anymore, right? So what can we use instead? Drift chambers, right? We use drift chambers or other similar technologies that are cheap and easy to produce and don't have that high resolution because they don't need that high resolution, right? So we use those on the outside because we can, right? And also because we must, because it's expensive to build anything out here, right? So you need to use real cheap materials when you're building on this big a radius, right? Okay, so the very simplest thing you can do is just see, do I see a particle at all, right? Which could be a drift chamber, right? And that would be the simplest muon detector. However, modern or contemporary accelerator detector designs have realized that you can do more with a muon than just say, hey, there was a muon. What could you do with it? That's crazy. It does not do that. But what can we do with it? We can measure something about it. We can't measure its energy, but we could measure its momentum. Now, you're like, didn't we just measure its momentum? Yes, but we measure its momentum inside a very constricted environment where it's surrounded by a billion other particles, right? So now we have a chance to get a nice sort of leisurely measurement of its momentum, where it's way far away from everything, and it's all spread out, so you don't need to, cram everything in there, and you can use cheap stuff to do it. Okay, so as a result, modern and some of the older ones as well, come up with a way to actually measure the momentum of the muon again. Basically, the momentum measurement here is going to be better than the momentum measurement down here, and so you can use that to improve the quality of your measurements of muons, making muons like the awesome superparticle now, right? Instead of being like, oh no, we can't measure them, now we're like, oh wow, we can measure them twice, making them our best particle now. Yeah?
Since there's not a magnetic field around the thing, how do you find the radius?
What a good question. How do you measure it without a magnetic field? That's a good question. I'm glad you asked that. Someone have a thought? You need a magnetic field to measure momentum, right? That's what we did before. So, what would we do? Put in a magnetic field. That would be the one thing you can do. Now, the standard way of doing that, okay, you are not going to build another solenoid.
Thank goodness.
That would be ridiculous. I mean, you could try, but like that would be so incredibly expensive, right? To try and surround like it's insane, right? So you're not going to build another solenoid. So what you have instead are, okay, these are a little hard to draw. We have a set called toroids. You guys know what a toroid is?
Yeah.
Toroid is related to the word torus, right? A torus is a donut shape. A toroid is anything with a hole in it. It doesn't have to be shaped like a donut. In particular, the toroids we use, so toroidal magnets are like a donut and the field goes through the middle. Okay? What you can do is you can so you tend to do them like this. Okay, this is a toroid.
Wait, are we seeing this or Atlas?
So you notice it doesn't look like a donut really, it looks like a big square, but it's an empty square. Okay, it's a hollow square that just has, I mean, this thing is like this, right? You need the actual magnet looks like that, right? So the magnet is like a big frame. Okay? The magnetic field goes through it. And then what you do is you have multiple ones of those going around the detector. This is hard to draw. I'm no good at drawing, as maybe you noticed. But if you're looking at the front view, okay, then a toroid seen head-on looks like that. You see what I'm saying? Right? It looks like this from the sides, from the front it looks like that, right? Do you get that? Okay, then you put toroids going around like spokes. Because the magnetic field goes through the toroid, right? So if you put a bunch of them around like this, the magnetic field will go through it, and that's, now you have a magnetic field.
Oh.
Yeah.
How would you accomplish this in a spherical manner?
That is a very good question. The answer is you have to do something like this, right? The difference is that from the side, it would not look like this. Probably you break this in. Right, like a hat. Probably easier to have a few of them. Like that roughly follow the outlines of the sphere.
All right.
And then each one of those replicates going around.
All right.
Like a box.
Now, the reason you do it, the big advantage of this kind of toroid, which they call airport toroids, because there's nothing in the middle. Okay? The big advantage is, first of all, it's easier to build things out here. Infrastructure is no problem. These things are cheaper than solenoids. And you get all the space you need, right? The advantage is now you can put in your muon detectors in the middle because it's empty in the middle, right? So what you typically do is you put your detectors before, during, and after the field. Okay? That's your standard design is you have some detectors before the magnets, inside the magnets, outside the magnets. That's the standard design, yeah.
So that would be your 3 points to make sure it breaks.
Right, and typically you actually put a few layers in each just to help reinforce it. But yeah, this gives you 3 points that you can use to get that momentum resolution, which is cool. Okay, and now you can measure the muon's momentum twice, and the second one's better, right? And combining those together, you get a really good measurement of the muon, plus a very good identification rate. That's to say, it's very hard to fake a muon now. So now muons become our favorite particles. Yeah.
But it still begs the question: how do you find the mass?
You know the mass of muon.
What?
You know the mass of muon.
Look at that document.
Oh yeah.
Yeah. Just as only muons get there, so now we don't need to know the mass.
All right.
Yeah. Because you know the mass and you know the momentum. Oh, yeah, there you go.
How exactly do you do this?
So the particle going through will hit here, here, and here on its way through. But it will curve while it's going through the magnetic field. Right? Therefore, you can trace out its trajectory. Now, you could do more than 3. At a minimum, you need these 3. Right?
So the one in the inside report is like right in the center. So
That's one way to do it, right? And then you can trace it through. Now, you could certainly have more than that, because that will give you more sort of handles on where it's going. That's the basic design, yeah.
Okay, so these little toroids are shaped like boxes, right?
Yeah, gigantic toroids, but yeah.
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 So how are the detectors going to run through the thing without the boxes interfering with
They're
different?
shaped like frames. Now, it's
Yeah.
true that there's, I mean, you kind of get in the way in some place, right?
Yeah.
That's why you don't typically build it solid with detector through here. You typically just put some here, some here, some here, because you have all the space in the world, right?
Mm-hmm.
So there's no, I mean, it's true, as it goes out, it gets more expensive. You're using cheap detectors. So you usually just leave some space. But yeah, like right here, it will get in the way of your detector, right? And so, yeah, then you don't build there, right? So it's not, I mean, so yeah, there are places that could have, that have, this has to run through it, and that'll cause a hole and stuff. And yeah, you can just, but you can get the trajectories and still work your way around it. Yeah.
Are there typically a lot more than these 3?
They typically put them, yeah, there's typically more than 3, not necessarily a lot more, they usually kind of bunch them, like they'll put 4 layers right next to each other so you can get a direction on it, and then put another 4 layers up here, and like they'll kind of put it in clusters of 4 or so layers. Again, the cheap stuff, not silicon, right? Okay, so that's now this is the standard sort of conventional design of a muon detector. You just put shielding in, which is your return yoke. You put these big airport toroids. You put measurements in there. Now there is one thing. It tends to make your detector very. What did you say? Big. Yes, it tends to make it big. Somewhat expensive, but it's more that the size has an impact on your budget. I mean, you have the same budget, but now you're making it big. That affects what you can spend on the things themselves. So there's an alternate design that I'll mention, because this is virtually identical to the design of the Atlas, the Atlas detector at the LHC, which Atlas, I told you about what Atlas stands for, right? Right?
Large coronal apparatus.
Sorry. Atlas, the world's worst acronym, even worse than NCSSMST, which is a bad acronym. But this one's even worse, because Atlas stands for A,
Large.
toroidal, LHC, that's right, the L stands for LHC, apparatus. Right?
Wait, what was the thing I
A toroidal LHC apparatus, which could be a watch as far as I can tell. I mean, that's shaped like a toy too, you know? It's like a stupid name.
as you
It's toroidal because toruses in it. That's the name. So it's not even a toroidal, it's cylindrical, but it has toruses. Okay, so this is how Atlas designed it. Atlas, they just wanted to call it Atlas because it's huge. That's why they named it Atlas. It's gigantic, it's 8 stories tall, it's massive old things. Most of the pictures, if you look at pictures of Atlas, you can see the toroids. These giant, you can see, they usually do the front end picture, and you can see the huge pipes. They look like giant pipes. They're actually toroidal magnets that are running. You can see them looping around and coming out like that, going back like that from the front end views. The classic view of Atlas, which is with the core removed, is a really pretty picture. You can see all the toroids wrapping around on the sides. Those are the toroids. Now, the other experiment is called the compact muon solenoid experiment, or CMS. That one is compact, so it's only 6 stories tall. It's a pretty big game. But it's actually a muon. I mean, muon solenoid is not actually that name for it. Like it's a regional acronym. CMS is a clever strategy. CMS is built on being clever. It doesn't necessarily work better, it's just clever. So CMS, Atlas did a very traditional tracking chamber with silicon on the inside and multi-wire on the outside. CMS does it with all silicon, right? Atlas does a very traditional, does very traditional sampling, ecal and hcal with brass and plastic insulator and the usual stuff. And CMS does a homogeneous lead tungstate ecal with liquid argon end caps, and then a pretty conventional hcal, all inside the solenoid. So the whole thing's inside the solenoid.
What?
Yeah, because that way there's nothing in between your tracking detector and your calorimeter, so you get better energy measurement. But it makes it more sensitive. And then to tap it off, they have this really clever way of doing the muons. I think it's really cool. Here's what they do. This is a front view again. Okay, so here's CMS in all its craziness. And the outer layer now is the solenoid, right? The big solenoid. And a very high power one. Atlas inner solenoid is 2 Tesla. CMS is 4 Tesla. It's very strong mass. Very strong magnet, very large. Okay, here's what it does. Right around it, it puts a return yoke. Okay? But the return yoke, which I will indicate by putting it, so it's a big chunk of iron, right? The return yoke is layered. Wow, this is hard to do. Let me draw one segment of it. Will that be okay? Okay, so this is the detector. You know what I mean? You see what I mean? I don't want to draw the whole circle, it takes too long. So here's the solenoid, right? Then here's return yoke. But the return yoke comes in layers, like this. You see that? So it's a big piece of steel, but it's got holes in it going around. Okay? I mean, obviously the little places for structural support that to be in there, but basically it's got big holes running through it. Okay? Why do you do that? Because now as you do that, the magnetic field from the solenoid doesn't disappear right away. It falls off gradually as it goes out. Okay, so magnetic field here is not 0. It's like, if this is 4, here it's like 2, here it's like 1.5, and here it's like 0.7, and then it goes to 0. Okay? So as you're going through the return yoke, the magnetic field drops off gradually rather than all at once. Why would you want that? What can you do with those holes there? What do you say?
Get more readings.
Right, what are you going to put in there?
Detectors.
Yeah, you put the detectors inside the holes, like that. And so now it's going through the residual magnetic field, and when it comes through here, the magnetic field makes it bend, right? When it goes through here, the residual magnetic field, reversing direction, makes it bend backwards. And so now you get one bend from this part of the solenoid, and then an opposite bend from the other part, from the return yoke from the solenoid. And then you can use that to to measure the momentum without needing a second magnet.
That would be a lot.
Well, yes, of course, but I mean, we have computers and measurements and stuff like that. We can do that part.
So this requires the solenoid being on the outside of the.
Okay, you can do it with the solenoid on the inside, but your calorimeter will be exposed to the full magnetic field still. Okay, so you still have to build your calorimeter magnet safe. Okay, either way, your calorimeter has to be magnet safe, and if you're going to do that at that point, it quite possibly is better to just pull it on the outside, so you have fewer radiation lengths between your tracker and your calorimeter. Okay, so that's a clever design. I think it's neat. Now, you don't get bonus points from that one because they already came up with it. But it's an alternate design. So this is sort of the standard design. This is kind of the crazy, like, hipster design. It's not quite hipster. I'm not quite sure what the word is. And those are both fine. As far as technologies to use, drift chambers are the cheapest, super cheap. And so you can certainly use those. There are also intermediate technologies that are sort of in between drift chambers and multi-wire. Multi-wires are not that cheap, you know. And stringing them up that scale is kind of crazy. So there's sort of these in-between ones that are sort of like low-resolution silicon that's cheap. They're called cathode strip chambers. And resistive plate chambers. And they both run off the same base. They both run a lot like, sort of like a four-man multi-wire chamber, right? You lay down a bunch of strips that are fairly close together, and the neon going through will hit them, and you'll see the hit. And of course, what you would always do is do multiple layers with strips running at 90 degrees to each other, right? The only difference is one of them is higher resolution and more expensive. One of them's lower resolution, right? And then the cheapest and lowest resolution of all is the drift chambers, which I don't think there's any way to get any cheaper than that. Okay, so the muons are always kind of like the afterthought. In fact, in my experiment CDF, the muon detectors were actually an afterthought. They actually put them on, and I'm like, wow, our muon detectors suck. So they realized they needed much better muon detectors. They added in the shielding steel, they put in more muon detectors. But at that point, the cavern itself, which had already been built, was not big enough. So they had to basically squeeze muon detectors wherever they could put them. So they're in like a really weird geometry because there's only so much room in the cavern they had done. They could just like stick them like in corners and places just to try and they just kind of started throwing them on every like piece of steel they could find. Like, all right, put the muon detectors here too. Because they're cheap, right? But you gotta have room for them. Anyway, nowadays we plan for this in advance and build the caverns nice and big so that there's plenty of room to move around. You'll see, when you see D0, there is no space anywhere. Bad design. When they built CMS and Atlas, there's a ton of space in the cavern. That gives you plenty of space to move things around. All right, so those are the basic parameters. So because of that, you only have 1.5 billion to work with, which is plenty because these things are cheap. You're not going to be using pixels, right? I'd like to see you try. I put in there a note about how many toroids you need to sustain a field of a given strength. Okay, basically the higher strength of the field, the closer the toroids have to be. So Atlas, for example, has 8 toroids going around, okay, to maintain a 2 Tesla field. But it depends on your outer radius of your toroid and the field strength. And I gave you a very simple little equation you can use to figure out how far apart your toroids have to be to maintain the field. Yes?
If you do the layered method, do you need the toroids?
Yeah, if you do the layered method, you don't need toroids. You need a lot more iron.
It's iron.
So, I mean, depends. You have to fill it with iron, whereas the toroids are just spaced out, right? So I just assumed, rather than have you indicate every single drift chamber, I started out by doing this, and I was like, this is going to be a very long Excel spreadsheet. So instead of doing that, you should just have everything in, sort of like you did like the calorimeter, or even the silicon, really, right? Just you put something, and I assume you mean a layer covered with that detector, right? So you put cylinder of drift tubes, and there'll be like a whole cylinder full of them, right? So you don't have to do it. Ditto for toroids, I just say put toroids in cylinder or sphere as needed. Probably cylinder is better for this one. And just fill in, I give you instructions, but you just fill in the strength and the number of toroids you want. and then we'll space them out with it. Okay? So hopefully things are clear enough. I don't have the visualizer ready yet because kids were sick this weekend. But they're getting better, so hopefully they'll have to be ready soon. But I mean, the basic, honestly, I don't even super need the visualizer. It's not that complicated stuff, right? The only thing is, you do want to make sure to do something at the end, right? Because you have to go this way too, and at this scale, right now, there's actually a lot of angle out here, right? So do make sure to fill in something on the end caps as well. Typically, you do the same kind of thing. Discs going this way, so like you do a power limiter or AV tracker. Discs going this way, and put a toroid out here too, or something. Put a toroid around here too, or something like that. That's standard thing. Okay? All right. So this time it's for you to get to work. To split the jobs are basically the same as for silicon, and they should be easy because you already know how to do it. Right? It should just be a matter of decide stuff to do, crank it out, and get it done. That's what I want to happen.
I'll do the same thing.
I don't want to be giant.
I'll do the same thing you guys want. Okay.
Considering the fact.
You want to start
So the number here, that's what we'll do. Yeah, you could always just check it. We have to have
Okay. Description, spreadsheet, and resolution.
Did what last?
You mean
here?
Here was still. Protector I know, right?
Yeah,
I actually really used spreadsheet again because it was control over when I got my stuff.
No, if you end up with this final design, you might, for the final project, you might be
I might have to spend my night.
Yeah, just do it. It's true, your Hadronic would have to be magnet safe now, right?
I was like, but like that's
It's like all the matter.
Why can't we use the money that we have?
This is all really
I know, if we had the money
certain
that
amount of
we
design
have,
here.
that would be so great. Exactly. I got a chance to do that.
Ask it as you can sit there.
yeah, we might be able to. I mean, let's see. The thing is, our soul noise would have to be. What was our Tesla?
You can just set the shape to sphere.
I'll have to look at it. You have Let's see, that would be not really 200,000 per Tesla per minute. 1 meter per second. That's 600 meters. That's 6 meters. That's what I was thinking. But where would it be written?
I don't know. So how do you not know? Someone told me.
No, where's your work? Your work at it. Where we?
Yeah, that was like
Okay, where would that be? There's 700 Tesla. That's what you say. Oh God, we may have made a critical error.
I mean, it's always nice, but especially given the time and stuff.
Well, maybe. Yeah, we won't be able to use it. That's 70 meters. 70 meters.
No, that doesn't make sense.
It doesn't.
That does not make sense. No.
I was given those me one time. It would make them
Okay. 42 centimeters.
remember.
Yeah, no. What I said. What are you doing? It's already perfect.
It is 700. I said it apparently.
Better higher or
Then we don't be able to calculate 220 TeV. I wonder if we can alter that now, because honestly the part 2 we have is massive now. Well, we have an issue.
Oh no.
Here's a solenoid strength of our field, 700 Tesla. Here's the size. Here's the size that it would be at 70 meters.
So yeah, we think that we think it's supposed to be 7.
And 8
So our total TV for our
Alright guys, you know who are talking about?
Yeah. And then we'll figure out but we won't. But you can't. I'm gonna ask you if we can do that.
That would be so.
Never mind. You get this actually worry about it. I think you will revise things.
That would change my.
I apologize.
It's like one massive spreadsheet of just like it'll just type it.
But if we don't do this now, it's gonna be insane.
And then the iron will also have 0.9 meters.
I love that extra credit.
Yeah, good luck.
Where did we get the solenoid strength of 700? Is that just for a random number?
CMS uses 4, that's bigger than ours, right? So,
I think it's supposed to be like
That's absolutely. Okay. So you remember those min-max of maximum strength? Yeah, those were supposed to be for solenoid. So we have 9 to 13.
well, that's like, you can't intersect that.
So if we can replace it 713, yeah. Probably will.
Yes. Technically, it's for little fuel.
Actually, 14 would be nice.
For you guys, we're going to turn you.
He already said 713 was like. I'll put the point.
You know what?
You get about half of
You know what? Fine.
We're not. Oh, you're not. We're going to try it. Okay, let's use it. Try it. Okay, that's fine. Wait, so.
Flip the coin. Your decision be nothing.
Just do it. Just be like
I'm like,
different, but it's.
For some reason, my sticky key popped up. How did you turn that back on?
I'm a TV.
I'm a genius.
You can measure. TV is 60.
Alright, so who's gonna do the
Wait, 60 TeV?
Yeah.
For what?
Your face.
No, for what part of Oh, no, wait. 20 TeV.
20 TV. A third, are we doing? So like, you don't even do that.
We would need 7. About 7.
That's fine.
So but we should always go. We always go max 1 billion. Plus an obscene amount of extra money.
Steve,
You will never guess what just happened.
You
Total
got it.
fortune. My total cost before I made a change was 12 billion. Guess what it is now?
2.
2 billion.
I was right. Can I get? Do I get a prize?
Yes.
What do I get?
0 points of extra credit for
No
ModPhys.
thanks.
Okay.
I'll do that. Alright, I'm gonna see if I can increase that a little bit.
Add 0 divided by 0 to your
Will 0 divided by 0 be 1?
It's undefined. Actually, no, 0 divided by 0 is like
You can't divide a number by itself. It's not how this works.
Is 0 divided by 0 what?
Actually, yeah. I think
Get right.
like 1 divided by the 7 is 2 turn 1 and 1/2.
Well, yes.
Instead of 1.
But you can't do it with something that's an unending set.
Are we really?
You can divide anything by any
Unending set.
You do know anything that's not
Which is the reason why if you divide 1 by 10, you're at infinity. It's the same number.
That's okay. All of the numbers are
You know what? So you're saying 1 over infinity was infinite? You're saying
Here, 1. Which is larger?
all numbers multiplied by all possible.
Or
What are you doing?
All real numbers equal negative 1/2.
You froze my computer!
How does that
it
happen?
doesn't matter whether eventually they'll use the same number.
What did you froze my computer? Try to type all of your notes. Oh, there we go.
Wait, Benji, I have a program that I will use on your
You're gonna into
It's raining.
So, do you want to see my program?
it depends on the program. I'm blaming you. Even though it's been happening for the last couple of weeks, it's not really. I have Control Delete now on the first tab.
Yes, that's the program. No, I don't want to. I don't listen to hear it.
Oh, that's the problem that you don't do.
So it's not picked. Yeah, it's not picked up by any antiviruses. That's the best.
What?
And it'll crash under a second.
How? Who created this? How does it do that?
So it kind of it overloads it basically by opening so many things.
Oh, it's one of those.
Yeah. It's not necessarily original, but it gets the job done.
Efficiency over creativity.
Don't tell me that.
Wait, we need to get this on his computer.
No.
Just every time, no. I have it in its startup
now
operation, so every time it opens.
Oh, 7 custom.
Okay. 0.7 meters.
Imagine the
that. 0.7 meters thick.
Total detected so far is 2.1.
You might be able to use some fixes.
We might be too.
I think Dr. Don might kill us, but you know what?
You know what? I'm
Let him.
You're not my mom.
Tell your mom to stop.
You can't.
Listen, my mom is a very loud person. Why is this name Excel again? Oh yeah.
Remember to do it as shield.
Excel. Listen. How cute.
That's like really
Where's
bad.
small child? I didn't ask you to speak.
You're not a child.
Small child compared to me.
No. You don't know me.
You're bigger than you know me.
That's not false.
That's good. That's a great problem.
That was an odd way of phrasing that.
That table basically has their second child.
Think about that sound. God, having such large radiuses is not small.
Radia.
Oh, I forgot.
Must you be
Ours. Is
this
this
way?
ours? Yes, that's me. Where is... I need radius. Where's the radius of our sphere? Oh, what's the radius of our sphere? What sheet is it under?
The radius of everything inside the solenoid is like 0.35.
It's, okay, 0.35. With the solenoid, it becomes 1 meter thick.
Actually, exactly.
Almost exactly.
That is
1.0479. What?
So I increased
So we need, okay. How much, magnet? Such a magnet. Is iron absorbent.
How much magnet is iron absorbing?
It was pretty good.
There's reviews for the CMS detector. There's like an application on Google. The service was terrible. The price was
That's good.
Aiden,
What?
you should not be having this much fun.
You shouldn't be telling me what to do. I have my copy of QED. I get to rant about Richard Feynman to people who don't actually care. Would they let me rant anyway without ranting enough?
Yeah, that's why I'm here. I'm here just so you can do that.
Wow. Then why aren't I?
Because
I'm very bad at my job.
Why is your computer frozen?
Because
you're touching it. But you hear open depth on my computer.
I kind of want to open that one.
Did I tell you about the time Richard Feynman cross-dressed as Queen Elizabeth at 13th at a party?
So the thing is, it works in a logarithmic scale too. Because it opens
Oh my
itself.
god! Oh my god! That's beautiful!
That's so I was kind of happy.
Did I tell you about the time Richard Feynman filled his room with ants?
Did I tell you the time Richard Feynman died?
Okay, you know what? His last words were hella emo. You know what they were? I hate to die twice. It's so boring. He was such an edgelord.
You wish you did.
He died when he was 69 years old, which I think is very fitting.
What a
What?
Okay, just so you know, guys, you cannot be using
Yes, you can.
Why? He lied to us.
No.
This is
This is the final time.
No, after this we get to revise everything and then present it to the class. Which, that ought to be fun.
Why
And you
can't we
both,
just
you
do
guys-
that now? It's so much easier.
That's not the point. Anyway,
What is the point? There's no point in anything. What's the point in modern physics? It's just to have fun.
Actually,
Physics is like
it
sex.
does
It may
have
yield practical results. That's not why we do it. That, my friend, is a quote by Richard Feynman.
I know.
Eden,
What?
are you Lindana and you just want to have fun?
Who? Are you putting references?
Yes.
This is ModPhys. You're only allowed to make, the only meme references you're allowed to make are about Dirac and Feynman. That's it.
I can make a lot more references.
No!
Thank you very much.
Did I tell you about the time?
Richard Feynman died.
Okay, wow.
What were we saying about the
Too
time?
soon, that was 1981.
What were we saying about the time that Richard Feynman was accused of being a professional spy for the?
That was so many times, and then he ended up being friends with the spy. That was hilarious.
Hilarious. He almost got his entire
You know what else
career
is hilarious?
placed on lighting room.
Your life.
The time Richard Feynman died.
You know what else is hilarious?
The time Dirac died.
The time everybody was like, hey, maybe we should kill Richard Feynman. He's like an idiot and he keeps messing around. He's like doing all this thing like real bad. Richard Feynman was like, LOL, nope.
Anyway, it's a point where you need to test
Damn it,
how
I'm
much
only-
iron absorbs in a cake. So how many layers of iron?
37.
We're gonna have like a big ring in the middle.
No.
Yes, yes, I approve.
We actually have any choice.
You have fun.
this mine?
No, it's just sitting there.
All right, let me see if it has the same security numbers.
The mini water bottles from Sodexo are so weird. Have you smelled the water bottle? It smells really good.
Alright, now the class is over. Remember, this is the last time I'm going to give you. This should be pretty straightforward. I want it to be straightforward. You can no questions.
I'll send it to you.
Is it going around the beam?
So what do we need, by the way?
Money.
So the beam pipe.
We're gonna have 1.5 billion, and
We don't have enough.
you're gonna have 500 million.
What about like the 2 million from the accelerator? Why not?
Yeah, good.